Hey, welcome back. In today's video, we are going to see how we can check Linux disk usage in Ruby. Now, to follow along with this video, make sure you have watched the previous videos about the Ruby C extension because we are going to write C with Ruby. Otherwise, it is possible with some gems only, okay? So we need better planning how we can check disk usage. Luckily, we have a C library called statvfs.h which can return the disk usage by means of block size and free block size, available block size, and so on. So without any further ado, let's search for sys statvfs.h in Google, and you can see that we have these guides here. I'm just going to follow the man7.org page. Here, as you can see, we have to include systatvfs.h, and also we will have a struct statvfs where we will have these members. So to start off, let's open our terminal and let's create a new directory called statvfs, and then cd into statvfs, create our xtconf.rb and require mkmf, and then create makefile called statvfs. And now we need to make our C file called, maybe call it statvfs as well to keep stuff simple. We will need to include sys statvfs.h first. As you can see here, we need sys statvfs.h, and then we have to define our main function here in C, but we have to remove that in Ruby, for example. Now let's create the struct statvfs and let's call it buff, short for buffer. Now we have to call the statvfs function with the first argument, the directory name, and the buffer. Okay, so we will need to pass the address of the buffer, not the buffer itself. So it will copy these values over the buffer. You can call the buffer anything you want. And now let's do printf %d, and as you can see, we get unsigned long for the if B size, which is block size. For most of the SSDs, thumb drives, flash drives, the block size is most likely going to be 4096. So probably that's what we are going to see, and we have to do buff dot, remember we have copied everything to buff, and we have to get the if B size member from the buff. And as you can see, we haven't included stdio yet, but we have to do that. And that's it. That's how you can simply get the block size of your file system. Now if I compile and run this code, to compile we need to run gcc statvfs.c && a.out. Okay, so we have a typo here. Sorry for that. We missed the T here. Now if I compile and run our code, we get 94,096 as expected. Now let's also check the other members. Let's have some dashes here, shall we? Let's not call multiple printf here. We can just go with one, and we will have %d for the next items. Now let's check the maybe the number of free blocks, which is multiplied by the blocks will give you the free space. If I do b free as given, and also available is the available space of the hard disk drive or the storage, maybe the file system, sorry. So as you can see, GNOME system monitor currently has a bug here. As you can see, it shows the bars like that, which is really annoying. But as you can see, I have 38.3 GB available. So if I run this code, okay, so we need to first modify, of course. We need to do be avail here. And if I compile and run this code, you see that we have 4096 blocks, and the available and free space are here same, but it cannot be same for various reasons. Do not call free as available and available as free, because that erroneous. On many system you can see that you have different block size, and also the free blocks can be totally different from available blocks. If I launch IRB and if I do 4096, which is the size of every single block, so it is 4096 bytes. If I multiply that with the free space, we get 38 something, okay? And if I divide that with maybe 1024 times 3, I believe, as you can see, we have 35 GB left. But on GNOME system monitor, as you can see, we have 38.3 GB free space and available space, because they are using the 1000, not 1024, which is this is actually the gigabyte and this is gigabyte. So as you can see, we have the GB here and not something like GIB like this. As you can see, here we have GIB, which is gigabyte, but here we have gigabyte. So we get 38.3 GB available or free space, which is same for us. That's how you can get the free and available spaces. Now let's convert our statvfs for Ruby. To do that, I will just remove the main, because which is defined in ruby.h somewhere. We will do init and call it statvfs, and rather than printing, I want a hash here. To create the hash, oh sorry, we need to include ruby.h with double quotes, and we'll define the hash here called hash equals to rb hash new. As you have seen in the previous video, we can create hash with this function, and rather than printing, I'll just do rb hash asset and pass the hash here, give the string rbstr new cstr, and pass maybe the block size, which we will call b size. We also have to convert this fb size into a Ruby object. To do that, we'll do, because it returns unsigned long, we have to do u long to num, and then the buff.fb size, and we can just comment out this printf here. And now later on we will create functions. For now I'll just do rb gv set, call it $a and set it to hash, and rb global variable, and just pass the hash here. Now it should compile and run our code fine. Okay, fingers crossed. Let's compile our code. Ruby xtconv.rb ampersand ampersand make ampersand ampersand ruby minus r, and we'll get statvfs.so. We'll print $a. Make sure your quotes are single, because otherwise $a is a bash variable. As you can see, we have b size 4096. We don't want string here, we want symbol. To convert it to symbol, we'll do rb intern. And if I just compile and run this code, you can see we have something gibberish number here, which has no meaning to us. So we have to also do id to sim. And if I compile and run this code again, as you can see, we have b size, which is set to 4096. And then we'll just copy and paste this 3 times maybe, and we'll have something like what we had here. We have block free and block avail. So we will have b free and be avail. We can also separate that with underscores. Now there's a problem. The number of available blocks is actually fsblkcnt, which is maybe fs file system block count type. Okay, so we need to convert it to unsigned long. To do that, I will have to, of course, I have to remove this, right? Be free here and be avail here, but we want the unsigned long. We can just do this. Now it looks very ugly, as you can see. Of course, I need to resize the terminal, but we'll later on prettify this code. And make sure we have u ll to num instead of u long to num. And if I compile and run this code again, we get the be size, be free, and be avail. Now let's prettify our code a bit, because this is really unreadable. Now this code is readable, but it has more lines, right? So that doesn't matter. We need, it doesn't slow down your code, so it doesn't matter how many lines I'm using. I may be using 50 lines, but when I compile this code, I always get the optimized version. So in GCC, for example, you will pass minus O3 for the highest level optimization, and then it has the O fast, which breaks sometimes, and it is the most maximum level optimization. And also it has OS, which will compile your code for the size. You don't care about the CPU and maybe the resource usage and performance kind of thing, and it will just make the program smaller, no matter how. Okay, so we have this code here, which should run probably, and if I compile and run it, yeah, we get the same thing back. Now let's remove all of this, and we don't want to hard code this value here. We want to pass arguments. Okay, so we will cut it and paste it here and call this function as maybe value statvfs. It will return a Ruby value, which is the hash. To return it, we have to use return hash, and we can now delete the global variable set kind of thing because we don't need that, and it returns the hash. But we have the hard-coded path here. To remove that, we will take one argument, of course, value obj, which we'll just discard because we don't need that. And then we need to get the argument. Let's call it path. And we have one argument here, path, and we have to convert it to a C object. To do that, I will do character star, maybe call it P equals to, let's set it to, let's call the function string value pointer. I believe it is spelled like that, str value ptr. Then give the path here, which will get converted into our C character, and then pass the P instead of the hard-coded path. Inside int statvfs, we will define our global function called with rb define global function, and let's call it something like statvfs. We will call the statvfs function, and it takes one argument. If I compile and run this code, we have struct statvfs star here, which is okay. We need string value pointer and not str. This makes me all the time confusing, and I rely on the compiler error for that, which is really bad. I don't know why I forget the string. I always write str. Now we have another error, which is statvfs. We are defining the statvfs again, so let's call it statfs maybe, with the capital Fs, and rename it here statfs. And if I compile and run this code, we get nil because yeah, we don't have $a here. We have to call the function statvfs. We have to pass the argument, which is the root. As you can see, we have the block size, block free, and block avail. Now, if I pass the location of my thumb drive, which is okay, it is always confusing. I'll just run lsblk, and it is mounted here. If I copy and paste this code, do know that this is also a flash drive and this has the block size of 4096. If I now, okay, let's remove this because it looks terrible. If I first do a equals to statvfs and then a and then b size times a of, and get the b free here. If I print that, I get exactly that. Now we have to convert it to gigabyte. To do that, I'll just multiply that like this, and fdiv, which will just float divide, and divide that with 1000 to the power 3, or maybe 10 to the power 9, which makes more sense. We have 38.29 GB. It reduced because I'm recording this video, and also there are a lot of things going on in the background. And now if I give the path of my pen drive, the mounted location, we need to copy it again. As you can see, I have 2.37 GB left, which is the free space. Now, how we can get the total amount of space? We are getting the free space, right? To get the total amount of space, we can just get we have the block size, right? And we can also use the f blocks to get the number of blocks. Now let's edit our code again, and we have to copy this and set it to, okay, let's call it b free, b size. I'm just renaming it, doesn't matter. First I need b size, and then I need b blocks, and we will set it to f blocks with s here. And if I compile and run this code, I get same value, but we now have the blocks here. So this is the total number of blocks we currently have, and this is the free. So if I multiply this with the b size, we will get the total size of our disk. So in our Ruby program, if I do b size times b blocks, I believe, yeah, b blocks. As you can see, I have 31 GB thumb drive. You can verify it with this, which is here. We have 29.1 GB used, and it is total 31.5 GB. So if we just round this value to 2 decimal places, we get 31.47. Yeah, sorry, if we have to round it to 1 decimal places, and we get 31.5, just like this, right? So in the case of my root file system, if I do this, I get 120 GB exactly. So as you can see, we have 120 GB here, but if I just remove the round from here, I get a 199.98 GB because my solid state drive is 120 gigabyte. Now that's how you can use statvfs. We don't need to compile our code. We can just run it like this. We don't need to compile it every time, which is faster, of course. And if I just open my IRB and require statvfs and then write this program here, we get exactly 119. So I don't need to compile anything, right? And if I want to get the size of my, say, RAM disk, which is probably 6 gigabyte, I get 6.5 because yeah, it is 6.5, sorry. If I do TMP, I get 4.29. But if I do 1024 to the power of 3, I get exactly 4. If I do RAM disk here, I get 6 here. And if I give the mount point of my thumb drive again, which is copied from this, as you can see, I have 29.30. So it doesn't matter. You can just call this function from here. Now it will always run statvfs, and that code we compiled already. So this is quite fast. And if you just measure the time it takes to do that without the PA, because printing takes some time, I will do process dot clock get time, and then process clock monotonic. Why we are using this instead of time.now? Because time.now is kind of like wall clock. So yeah, it flows monotonically, but as you can see, we have some discrepancy, and it might not agree with the monotonic clock. So monotonic clock is the most reliable clock. We don't want the time.now, and that will be better if we just can get the CPU time. If you want to get the CPU time of every process, you will just have to read the S time, guess time, and you can just subtract that with the uptime and maybe the system start time, right? I'm not going to showing that in this video. Maybe that could be a future video, I'm not sure. And Linuxstat has that stuff implemented. You can just take a look at Linuxstat and read how the time is getting calculated. So if I copy this code, I have to paste that here because I need the start time. And it is always going to be more than this because this code is going to take some time. But if even if it takes 0 time, then clock get time, clock monotonic will be 0, which is not possible actually in most cases. It will be at least something, maybe some nanoseconds off, right? So I'll just do minus t. As you can see, it takes 1.377, very 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 small time. If I just multiply with 1000 and also 1 million, it takes 12 microsecond, which is too small. Do know that this is just getting the file system information from my thumb drive. If I again use the root, if I use the RAM disk, it is very trivial. It is very small amount of data that the function has to fetch, our C function. So it doesn't matter. It is just 12 microsecond kind of thing. So if you are using a million loop, that will cause maybe 12-second delay, which is quite faster, I believe. And we have this information, which is really valuable. Hope you learned something new in this video. You can just play with these things here: number of inodes, number of free inodes, and the free inodes for unprivileged user and stuff. You can just play with this stuff. I have just shown you how you can just implement the basic things, the B size, FR size, blocks and stuff. Sorry, I haven't shown FR size, which is the fragment size. You have to play around and you have to read that thing here. And also you have some more things which are used by Ruby a lot. You have also these things like stnodev, which is disallow access to device special files on this file system. So you can just control your Linux system with Ruby like that. You can not only control Linux system, you can also control Windows system, which is really exciting. So anyway, let me know that if you have any trouble with running this code. I'm not sure how you can run this on Unix or Mac OS or maybe on Windows. I have certainly no idea about Windows. I can guide you for Unix, like the FreeBSD, DragonflyBSD, GhostBSD, OpenBSD, and those similar ones. So that's it for today's video. Hope you have learned something new. If so, please press the like button. And if you have any suggestion, any constructive criticism, feel free to just write them down in the comment section. I'm always open to criticisms and suggestions so that I can improve my channel. So thank you very much again for watching. Hope that you have a great day.